Welcome back. This is video lecture 11.2, part 1. And in this lecture, we're going to prepare for lecture 11.2, part 2. And in part 2, we're going to learn a new way to calculate torque due to a force. But in this part 1, we have to introduce a little bit more about vectors in order that we can then proceed to studying torque again. So the reading that goes with this particular video lecture is actually going to take us way back into chapter 3. Chapter 3, to remind you, was all about vectors. And in particular, section 3 of chapter 3 was all about multiplying two or more vectors together. And we're going to go back to that. Now, we've already learned one way to multiply two vectors. And we called it the scalar product. We also called it the dot product. I like the name scalar product a little better myself because it reminds me in its name, scalar product, that the outcome of taking the scalar product of two vectors is not a vector, a scalar. But remember, we also called it dot product. Let me remind you just very briefly about that. Let's say we have two vectors, A arrow and B arrow, and we want to take the scalar product of them. I'll write it up above here. We take A, and then we write a big dot, and then a B arrow. That's how we're telling, that's why it's called often the dot product, but it really means scalar product. And so the rule for calculating the scalar product of two vectors was take the magnitude of the first vector, that would be the magnitude of A, then scalar multiply it with the magnitude of the second vector, B, and then scalar multiply that with the cosine of the angle we call phi, where phi is the angle between A and B when they're drawn with a common tail. In fact, you can look at my little drawing right below with an x and y axis and a vector A and a vector B, and they're both drawn with their tails together at the origin, so they have a common tail, and there it's showing you the angle phi between A and B. And this is how you would calculate the scalar or dot product of two vectors. Okay, now that's what we learned already. We needed that, if you recall, to calculate the work done by a constant force. Remember, work done by a constant force is force dot displacement. Okay, now, it may not surprise you, if you didn't already know it, to learn that there is a second way to multiply two vectors, such as the A and the B that we have drawn here in our diagram. But in this second way of multiplying two vectors, the outcome is not a scalar. It is a third vector, a new vector. And so this second method of multiplying two vectors is going to be called the vector product of two vectors. Okay? Let's talk about that. That's the point of this video lecture. How do you perform the vector product of two vectors? The name tells you what you get out. The outcome, the output, the result of a vector product of two vectors is another vector, a third vector. And so, here's how we're going to write it. Let's take those same two vectors A and B, okay? And the notation we're going to use for the vector product is right here. A with what looks like a regular multiplication symbol, and then B. But I want to emphasize most strongly that that so-called regular multiplication symbol between the A and the B is not a regular multiplication symbol, not even close. We are just using that symbol that you have seen so many times before. But what it means in this context, when it's between two vectors, is that you are to take the vector product of A and B. So the context is important. The symbol's meaning depends on its context. And when it's written, the multiplication symbol, when it's written between two vectors, that's a clear indication that it's not the old-fashioned multiplication. It's this new multiplication called a vector product. And in fact, physicists often call this the cross product, because when this symbol is used between two vectors in physics and math, it's called a cross. Not times, not multiply, cross. So a lot of physicists would say A cross B. What they mean is the vector product of A and B, or the cross product of A and B. And the result of that will be a third vector that we're going to label C. And that means, well, it's a vector. C has a magnitude and a direction. And we're going to have to be able to find both things correctly. Let me denote for you how we would write the actual vector equation. Let me write it over here to the side. C arrow is the outcome when I take the vector product of A with B. That's the formal way to write it. The vector product A cross B gives you a third vector C. And now what we have to learn in this video is how to find the magnitude and the direction and or the components of the vector C. First, let's focus on the magnitude. Okay? How do you find just the magnitude part of this vector C? I'm just going to tell you the rule. Okay? Straight out of chapter 3, section 3. It's written right here. But note, it is only the formula for finding the magnitude of this resultant vector C. And I try to be very careful in the notation. Look what it says. The magnitude of C equals magnitude A, scalar multiply magnitude B, scalar multiply sine phi, where phi is the angle between A and B when they're drawn with a common tail. Let's compare and contrast that formula with the one up above for how you do scalar product. Up above, I wrote the formula for calculating the scalar product, A dot B. And below, I'm writing the formula for the magnitude of the vector product, A cross B. Well, they both start with the magnitude of the first vector, A. Then they scalar multiply by the magnitude of the second vector, B. So far, this is exactly the same. Here's the crucial difference, as you can see. The magnitude of C is found by taking the sine of the angle between A and B, whereas the scalar product is found by taking the cosine of the angle between A and B. And it is the way it is, folks, but I can only tell you that, boy, does that cause confusion. So I'm trying to warn you now. Don't confuse these formulas I've got here for A dot B up above and the magnitude of C down below. Now, as we're doing vector products and we're figuring out the magnitude of the resultant, we use sine phi. But this picture over here I have is still useful. I've got an A vector and a B vector. I've drawn them with a common tail. I happen to put their tail at the origin. You don't have to draw it that way, so that you can see what phi is. Let's go back now and look at that picture some more. First, let me give you a word of warning. You see how I've drawn that angle phi between A and B when they're drawn with a common tail? That's how you should find phi. Do not, warning, do not take that big angle between A and B, 360 minus phi. That will not give you the correct answer for magnitude C. So be wary of that. Phi's got to be the smaller of the two possible angles between A and B. Okay, so if I want the magnitude of the vector product of A and B, I would take the magnitude of that vector, and what A could be any vector that we've learned so far. Position, displacement, velocity, acceleration, force, linear momentum, right? It's a generic symbol, but it could be any vector. Then I take the magnitude of the second vector, B, which is also generic and could be anything we've learned. And then I take the sine of this angle phi. Okay? Note then, think about the angle phi and how you could get the biggest result for the magnitude of c, or the smallest result for the magnitude of c. Just think about adjusting that phi in that picture. What value for phi would give you the largest possible answer for magnitude c? Can you tell me? Well, you have to know about the sine function, right? Sine of phi, what's the biggest sine phi can be? 1. What's the value of phi when sine equals 1? Did you say 90 degrees? That would be a situation like this. A is like so, and then B is like so. So that the angle here between them is exactly 90 degrees. That will give you the biggest magnitude C. Now tell me a value of phi that would give you the smallest possible magnitude of C. Think about it. What value of phi would give you the smallest possible magnitude C? Did you say 0? Because you got to know that the sine of 0 is 0, and that's the smallest magnitude I can get. That would correspond to the A and the B in the same direction. Yes, then the phi would be 0. So here's something important to note. When you take the vector product of two vectors in the same direction, you get 0. You get nothing. Zip. There is another possibility for getting 0. You see what it would be? Another angle that you could have between A and B that would give you 0 for the magnitude of C. See what it is? It would be if the A and the B were exactly opposite to each other. What's the phi in that case? Did you say 180 degrees? And the sine of 180 degrees is 0. So two vectors are in the same direction, sometimes called parallel vectors, and two vectors that are in exactly opposite directions, sometimes called anti-parallel, have magnitude C equal to 0. These are all very useful things to remember. Okay? All right, now, I've been talking quite a bit about how you find the magnitude of the vector product of two vectors. There's still another part to this vector, C. What is its direction? All right, and I'm just telling you this result. There's two things to know about the direction of C. They're both very important. Here's the first thing. The direction of C, there should be a C right there. The direction of C is perpendicular to the plane containing the original two vectors A and B. If you ever take a course called linear algebra in the math department, you will learn that two vectors drawn with a common tail like this form a mathematical plane. I've drawn the picture explicitly to help you see that by putting A and B in the xy plane. Okay? So, first thing I'm telling you is that when I take the vector product A cross B, the resultant, C, must be perpendicular to the plane containing A and B. It cannot be in the same plane as A and B. And in my picture, that means it cannot be in the xy plane. It must be perpendicular to the xy plane. Well, that narrows it down because that only leaves me two possibilities. As far as this two-dimensional picture is concerned, there's only two directions that are perpendicular to this xy plane, the plane of the screen. That's straight out of the screen towards me, or straight into the screen away from me. You see that? And in this kind of drawing, the direction that is out of the screen if x is to the right and y is up, like you see in the screen, that's the direction of the plus z-axis. Whereas the direction into the screen is the minus z-axis direction. Okay, so this resultant C can only be out of the screen, plus z, in this case, or into the screen, negative z. because it must be perpendicular to the plane of A and B. So we only have two possibilities, out of the screen or into the screen. So we need a way to figure out which it is of those two. And that second step, whether you determine if it's out of the screen or into the screen, is called, and if you've had high school physics, you might have seen this before, and it might give you a little bit of a chill. It's called a right-hand rule. And I'm not sure if this is true anymore, but if you were taught in the British system, you might have been taught something called a left-hand rule. And if so, I'm sorry, but in the United States, we use the right-hand rule. And so, warning on that one. Okay? I'm going to use RHR, not HRH. RHR, right-hand rule. Okay? And we're going to have to think three-dimensionally to use the right-hand rule. But remember, think in the context of my drawing there with the A and the B and the XY plane. All I've got to figure out from the right-hand rule is whether A cross B is out of the screen towards me or into the screen away from me. That's all I need to figure out. And the right-hand rule is how I'm going to do it. All right, let me try to show you how to do the right-hand rule with an animation, because in the video, all you've got is a little image of me in the corner, and it's not easy to show how to do it with my right hand here, right-hand rule. I'll do that in class. That'll be a little bit better. But let me go to a Wiley Plus animation, which is going to attempt to show you a three-dimensional picture. And it shows x-axis and a y-axis, and then it's trying to show you plus z perpendicular to the xy plane, basically coming towards us. All the three axes are labeled there. And in that drawing, the vector A, just like in the drawing I had on the picture, on the slide, is pointing along plus x. I just chose that for it's nice and simple. There it is. The red arrow is A, with its tail at the origin. The blue arrow, B, is in the xy plane, if you like, above A, with its tail at the origin. So A and B are drawn with a common tail. All right, so we know if we take A cross B, that the resultant, C, must be perpendicular to the xy plane. So it's either in plus Z, towards us, or minus Z, away from us. All right, here we go. Now the right-hand rule goes like this. You take your right hand, and if you're left-handed, I apologize. It's just the way nature works. It's not something that physicists have about, oh, I like right versus left. It's the way nature works. So you take your right hand, and you hold out your thumb of your right hand like you're going to hitchhike. Don't ever do that, by the way. It's dangerous in this day and age. But you hold out the thumb of your right hand like you're going to hitchhike. And you reach in and you put your fingers along the first vector, A, the red arrow. You stretch out the fingers of your right hand along the direction of A. Hold the palm of your right hand so that the palm faces B. And then, with the fingers of your right hand, you push A so that it lies on top of B. Note the order, A on top of B. A on top of B. First on top of second. First on top of second. The order matters. And you see which way your thumb sticks out when you push A on top of B with the fingers of your right hand. And when I do that, looking at the vectors in the animation, my thumb basically points towards me. That means it's in plus Z. So when I run the animation, it's going to show A being pushed on top of B. It's not going to show a symbol of a hand. And then it's going to show which way the C points. So here we go. We're pushing A on top of B with the fingers of our right hand. The thumb of our right hand points out along towards us, which is along plus Z. And that's this green arrow. See, it's labeled C. All right, so this mimics us pushing A on top of B with the fingers of our right hand. And the green arrow is the way our thumb would point, out towards us, which is plus Z. Okay? All right. So, back to this picture. In my drawing on the slide, the direction of C, A cross B, since my slide is clearly only showing X and Y, purely two-dimensional, Remember, plus c is out of the screen, so vector c in my picture here would be directly out of the screen. Now, I will give you a warning or a tip. Applying the right-hand rule for vector products correctly takes a lot of practice. It's just the way it is. Our brains really struggle to visualize this three-dimensional situation. So the only way we will get competent at it is by doing lots of practice, which we will be doing in class and on engagement exercises and on Wiley+. All right, more things to know about vector product of two vectors. If you want to be fancy, you can say this. You can use this language. The vector product is non-commutative. In mathematics, to commute two quantities means to reverse them. So if we're talking about commutation with vector product, like A cross B, it's just saying, look at what you get if you reverse them. Do B cross A. The point to remember about vector product is the order matters. In other words, the resultant when you do A cross B and the resultant when you do B cross A are exactly equal and opposite. And that's what this negative sign here means. A cross B is equal to the negative of B cross A. A cross B and B cross A have equal magnitudes, but they have opposite directions. The order of the two vectors in the vector product matters. Okay? Let me show you that in the animation. Okay, back to Wiley+. And now I'm going to reset the animation. Remember where there's the A and there's the B. And now we're going to reflect the B vector through the XZ plane. It puts it down there. Let me drag it a little bit so you can see it better. Okay? So I haven't changed A, but I've redrawn a new version of B that is in the fourth quadrant of the XY plane. Before, B was in the first quadrant. So now, if you like, the B is below A, not above it. What's going to be the direction of A cross B? This is more practice. See if you can try it with your right hand. Take the fingers of your right hand and push the A, the red arrow, on top of the B. Let's see what we get. Notice how we're pushing the red on top of the blue. We have to push down now. And our thumb points away from us when we do that. So the resultant C is in the opposite direction. Okay, let me show you. And I'll come back to this slide. Let me show you another attempt to explain, teach about doing the right-hand rule. Okay, here we have a series of drawings, which actually do draw an actual right hand. And we've got two vectors, A and B. They're drawn in a plane that to me looks like a kind of a tabletop to help you visualize the plane of the two vectors. You see the A and the B drawn there with a common tail? All right, and in this top row, going across, we're going to do the right-hand rule to find the direction of A cross B. First of all, it's got to be perpendicular to the plane of A and B. A and B are in the plane of this tabletop, so the vector product A cross B has got to be perpendicular to the tabletop. And so in this drawing, that would be either straight up from the tabletop or straight down. So how do you find out which is the correct answer for that direction? You take your right hand with the thumb extended like you're hitchhiking, like is shown right here, and you start with your fingers pointing in the direction of A. Your palm pointing towards B. And then, with the fingers of your right hand, push A towards B. That's the way your fingers have to push, to rotate. Okay? Your whole fingers and palm are attempting to push A on top of B. And look which way your thumb points when you're doing that pushing. Up. So straight up from the surface is the direction of the resultant C. Now that's if I do A cross B. Now let's look at the second row in this drawing, because now we're going to do, so that top row was A cross B. Now we're going to do B cross A. It's the same two vectors A and B. Now they're just drawing them from a slightly different perspective, because you got to look at it from this angle now to see it better. But it really is the same two vectors A and B as in the top row, and they're still on that tabletop. So the resultant of A cross B, B cross A, has to be perpendicular to the surface of B and A, to the tabletop, so it's either straight up or straight down. All right, now to get started, you take your right hand with the thumb extended like you're going to hitchhike. Point the fingers of your right hand along the first vector. Remember, I'm doing B cross A, so the first vector is B, but have your palm facing the second one, A. See how they have to draw it? The right hand? And it is a right hand. The fingers have to be along B, but the palm has to be towards A, so that you can push B onto A. That's what this image shows. The fingers of the right hand with the palm is pushing B towards A. And look which way the thumb points now. Down. So downward is the direction of C when you do B cross A. So when I did A cross B, C pointed up. That was this picture. And when I reversed and did B cross A, C pointed down, exactly opposite. The order of the two vectors in the vector product matters. All right, here's one more tip that's a very useful thing to know, but it kind of makes your eyes go a bit wonky because it's a weird looking formula, but it is very handy. It goes like this. There is an alternative method of calculating the vector product of two vectors, and you want to use it if the two vectors have been given to you in unit vector notation. The two vectors you want to cross, the A and the B. In other words, what if I tell you A in unit vector notation with its three components, AX, AY, and AZ? In other words, I give you that number, and that number with units, depending upon what A is. And then I give you vector B in unit vector notation, meaning I give you the three components, BX, BY, and BZ with their units. What if I give you the information about A and B that way, in unit vector notation? Then I want to take advantage of the fact that I know AX, AY, AZ, BX, BY, BZ. Well, you go straight to this canned formula, okay, for finding A cross B, which of course we've been calling C, which we can still do. C equals, okay? And I told you it's a weird looking formula. You can read chapter 3, section 3 if you want to see how they get it. But the physicist and the engineer is just going to say, oh, I just want to go to it and use it. It's a tool. And here's the result of A cross B. You've got to look at it very carefully, but when you do, you see there's a kind of a cyclical pattern to how the components are combined. You take A sub y times B sub z minus B sub y times A sub z, all times I hat. In other words, all the stuff in this first set of parentheses is the x component of the resultant C. You get the x component of C by taking the y component of A times the z component of B minus the y component of B times the z component of A. And you cannot change those components. You cannot switch them around and do anything with the order. You must leave it like that. Next, plus A sub z times B sub x minus B sub z times A sub x, all times j hat. In other words, everything in this second parentheses is the y component of the resultant C. And then plus A sub x B sub y minus B sub x A sub y. So everything in that third set of parentheses is the z component of the resultant c. We just use it if we're given a and b in unit vector notation. Okay, I'm going to leave you on this video with just a little bit of practice. It's not going to be class engagement on Blackboard. That'll be in the part 2. Just for you to practice, okay? Because as I said, we're going to need lots of it. We're going to give you a mathematical formula that, in Physics 111 next semester, will be a rather important one. Whoops, pardon me. I have to highlight. It's the formula for calculating the force, F, arrow, on a particle with electrical charge Q that's moving with velocity V in what's called a magnetic field B. Now, you don't need to know really anything about B. I'm just going to tell you the formula for finding this force. It's right there. Q, which is a scalar, electric charge is a scalar, times the vector product, velocity cross magnetic field, V cross B. Okay, so that's the formula we're going to focus on. Formula for finding magnetic force. We're told, for the sake of this practice, it doesn't have to be this way in law of physics, it's just for this practice, that we're going to limit ourselves to situations where the velocity of the particle is exactly at a right angle to this thing called the magnetic field vector. We are to deduce the direction of the magnetic field vector in these 3 situations below when the Q is a positive number. Now the picture shows me, let's look at picture 1. It's got an X, Y, Z coordinate system that I need to end up, it doesn't actually show the particle, don't worry about it, but if you want to think of the particle as sitting at the origin, that's fine. Okay? There it is, there's the particle. It's got this positive amount of electrical charge Q. We are to end up with a force on this particle that points up along the plus Y direction. The velocity at the time we took this snapshot was in the plus Z direction. What must be the direction of the vector B? Given the V and the F. Kind of have to be able to think about the right-hand rule because F equals QV cross B. Q is positive, a positive scalar. So to get the force, you take V cross B, which will give you a vector, and then just multiply that by the positive scalar Q. Well, when you multiply any vector by a positive scalar, you don't affect its direction. So to get the direction of F right, all I have to do is make sure that the direction of V cross B is right. And I get the direction of V cross B from the right-hand rule. So I have to kind of do a reverse engineering of the right-hand rule and ask, what must be the direction of B such that V cross B gives me the correct direction for F? So look in case 1. There's the V in plus Z. I need to get an F that's in plus Y. What must be the direction of B? It's all based on the right-hand rule. I'd like you to pause the video and really try this because you have to practice and then come back and we'll talk about it. All right. So what we're talking about is that V cross B must be in the direction of the given vector F. And we're given a direction for V. So we need to deduce the direction of B using the right-hand rule. So you just try different directions for B. Remember, B's got to be perpendicular to V. It's got to be perpendicular to V. So that leaves you the options plus X and minus X, plus Y and minus Y. That's it. So just try them one by one with the right-hand rule and figure out which one, there's only one, will give you the correct direction for F. Feel free to pause the video again if you want to. Really, really try. Okay, did you say that the vector B must point in the plus X direction? Because you got to take your right hand, thumb extended like you're going to hitchhike, fingers extended along V. That's the first vector, V cross B. Fingers along V, and with palm facing B, and then push with the fingers of your right hand V on top of B. And you will find that B must be along plus X. And then you will get your thumb pointing up along Y. Okay? So in the first case, the B must be along plus X. Practice again, please. Pause the video. Look at case 2. There's the particle. It's got positive charge Q. I am to get a force, again, along plus Y. But this time, at the moment we took the snapshot, the velocity of the particle is along negative X. What's the required direction for B? That must be perpendicular to V. So your options are plus Z, plus Y, minus Y. Try it. Pause the video, try it, and then come back. Okay, did you say the required direction for the B vector is along plus Z? Because then, take the fingers of my right hand, thumb outstretched, start with your fingers pointing along V, palm facing B, and push V on top of B, and your thumb points up. Okay? So the correct direction for B is plus Z. All right, one more to practice. And I'm not sure, but my guess is that the author did not intend for these colors of the arrows to switch. Do you see how they switched them? Before, the force arrow was blue and the velocity arrow was red. They've switched them now. I think that's just a mistake, but let's leave the labels where they are. Okay? That is to say, the particle Q with positive charge is at the origin. Its velocity is along plus X, and I want to get a force along negative Y. What is the direction of B? Must be perpendicular to V, so your options are plus Z, plus Y, minus Y. Pause the video, think about it, then come back. Okay, did you say the direction for B was again plus Z? Because now, take fingers of your right hand, thumb outstretched like you're going to hitchhike, but start out with your fingers along V, V's along plus X. Oh, I got to start out like this because my palm's got to face the B, and then I push the V on top of the B. And my thumb points down, which is the direction of the force. So again, B is in plus Z. I'll leave you with just one more statement that yes, the right-hand rule and vector products take practice. That's perfectly legit if it feels a little overwhelming. We'll keep practicing. In part 2 video, we're going to go straight into using vector product to calculate torque. Okay? But that's all for this video.